Hi, in this unit we're going to be talking about thermochemistry. And let's do a quick review from what we learned a few units ago. So first we know that heat is energy measured in joules. And the temperature will be measured in Kelvin or degrees Celsius. And room temperature is 25 degrees Celsius. Room and standard temperature is all 25 degrees Celsius. And we also need to know system and surroundings. System, which is a process that is under observation, and we have the surroundings, which is basically everything else but the system. Alright, and then we also learned about Maxwell-Boltzmann distribution curves, where, let me draw it real quick. We have cold gas, room temperature gas, and then hot gas. And then we have this line as activation energy. This is number of molecules, and this is speed. So as temperature increases, kinetic energy increases, and so does the distribution of this kinetic energy. And since we're looking at the probabilities, the areas under the curves must equal to 1. And notice how as temperature increases, the curve flattens. Alright, and then let's look at a heating curve. Alright, let's take water for example. We have solid, and then this is liquid, this is solid, and this is gas, and this is at 0 degrees, this is at 100 degrees. Over here it is heat observed, and over here is degrees in Celsius. And adding heat to our system may not increase the temperature because notice these areas where the heat will be used to break apart the intermolecular forces, which is why our temperature doesn't increase during these periods. And a good thing to know that during these periods, potential energy increases. Alright, time to learn new things. First, we have the first law of thermodynamics. And that is, energy can be neither created nor destroyed, but can be transformed from one form to another. Now, the energy of the system will change when you have a chemical reaction, a phase change, or if there's a change in temperature. And now these changes result in energy being transferred in or out of the system in the form of heat and work. Now, heat and work tells us internal energy. So here's the new formula we'll be learning. Delta E will be equal to Q plus W, where this is the change in potential energy and kinetic energy in a system. And we also call this internal energy. Q is a heat that is transferred into the system. Now, if it's going in, it's going to be plus value, it's going to be a positive value, and if it's going out, it's going to be a negative value. So Q is the heat being transferred in or out of the system. If it's in, it's positive. If it's out, it's negative. Now, this is work done on the system or done on the surroundings. Now, if it's done on the system, it will be a positive value. If it's done on the surroundings, it will be a negative value. This is because if it's positive, energy goes into the system, and if it's negative, energy goes out of the system, which is into the surroundings. Okay, now let's quickly look at endothermic and exothermic processes. First, let's review endothermic. Now, in an endothermic process, the products have more potential energy and less kinetic energy than the reactants. And if the kinetic energy of the product is less, then products are also at a lower temperature than the surroundings. Let's draw this real quick. Reactants, products. In terms of potential energy, product is on top of reactants. As the reaction progress, heat moves in the net direction from the surroundings into the system until thermal equilibrium is established. So in endothermic, it's surroundings moving into a system. The heat is moving in. Now let's check out exothermic. In exothermic reaction, the products have less potential energy and more kinetic energy than the reactants. If the kinetic energy of the products are more, then products are also at a higher temperature than surroundings. So let's quickly draw this. And this is the reactant, this is the product, and this is the reactants. This is still potential energy, and this is the reaction process. So in an exothermic reaction, the heat will be moving from the system out into the surroundings. So we're going to have system moving out into the surroundings. The heat, this is heat. How the heat goes, all right? The heat will be moving from the system out into the surroundings. Now, one last formula that you guys need to know is that P is equal to F divided by A, and P is pressure, F is force, and A is area. Now, delta V, which is a change in volume, is equal to A times the delta D, which is a change in distance. Therefore, work equals F times D. Work equals to F times D, where F is P times A, because over here, if you multiply A on both sides, cancel it out, P times A is equal to F, and D is equal to volume divided by A. Over here, D is equal to volume divided by A. So this equals multiply by delta volume over A. So A and A cancel out. So our work is equal to negative pressure times delta V. That is our work formula that we need to use in here, up there. Where's the formula? Oh, over here. So Q is a heat being transferred in or out of the system. This is a change in potential energy and kinetic energy, which is also known as the change in internal energy. And if this is positive, that means the internal energy increase. If negative, that means the internal energy decreases. And work is the work done on the system or done on the surroundings. And work can be found using the formula negative P times delta V. In the next video, we'll be doing some practice problems with all these new formulas that we have learned. Thank you for watching.